Right now, as you lie still, you are moving. Not the spin of the Earth, which is carrying you eastward at roughly 1,000 miles per hour, and not the orbit of the Earth around the Sun, which is pulling you through space at 67,000 miles per hour, and not even the journey of our entire solar system sweeping around the center of the Milky Way at 500,000 miles per hour. There is another motion entirely, one that is harder to explain and stranger to contemplate. You, and the Earth, and the Sun, and the entire Milky Way galaxy, and hundreds of neighboring galaxies, are all being pulled through space towards something enormous. Something so massive that its gravity reaches across hundreds of millions of light years. Something we cannot directly see because the plane of our own galaxy sits in the line of sight, blocking the view with a curtain of dust and stars and gas. Astronomers call it the Great Attractor. Welcome to Sleepy Science Stories. Tonight we are going somewhere that requires a different kind of thinking. Not the scale of a solar system, which is large but imaginable, and not the scale of a galaxy, which is vast but at least familiar from images. We are thinking tonight at the scale of superclusters, structures so enormous that a beam of light traveling at the universal speed limit would need hundreds of millions of years just to cross them. The Great Attractor is not a single object. It is a region of space, a concentration of matter so extreme that its gravity has organized the motion of an enormous portion of the observable universe. The Milky Way is being pulled toward it at approximately 600 kilometers per second, which is roughly 1.3 million miles per hour. A speed so vast that even when you say the number, it does not feel real. And yet it is real, measured and confirmed by multiple independent research teams over several decades. The discovery of the Great Attractor began with a puzzle, a discrepancy, a group of galaxies not moving the way they were supposed to. The astronomers who found this spent years trying to explain it away, and eventually they concluded that it could not be explained away. Something real was causing it, something massive, something hidden. If you are a returning listener, welcome back to the dark. If this is your first time here, you have chosen a good night to start. We are going to follow that investigation together. We will start with what you feel right now, which is nothing. Lying still, completely unaware of the motion you are part of. We will zoom out until the galaxy you live in is a speck inside a larger structure, and that structure is a speck inside a larger structure still. And at the center of all of that, quietly, for billions of years, something has been pulling. The Great Attractor is not a threat. It will not reach you in any personal sense, because the distances involved make that impossible. But knowing it is there changes something about how the universe feels, because everything you see in the night sky is being carried along with you, toward a destination you cannot observe. Let your breathing slow. Let the room settle around you, and hold the thought, just for a moment, that the stillness you feel is an illusion, that you are a passenger on a planet, inside a solar system, inside a galaxy, inside a supercluster of galaxies, and all of it is moving, all of it is being pulled, all of it is going somewhere. Tonight, we find out where. The Great Attractor is, at its heart, a story about the limits of what we can see and the power of what we can deduce. We could not see it directly for most of the period we knew it existed. We could only see its fingerprints on the motions of things we could observe. And this is a recurring pattern in the history of science. The thing you want to understand is hidden, and what you can access is the shadow it casts on everything around it, so you study that shadow carefully enough, precisely enough, until the shape of the thing casting it becomes clear. The Great Attractor was found exactly this way. Its mass and location were reconstructed from the velocity anomalies of hundreds of galaxies spread across a vast region of sky, long before anyone directly observed the galaxy clusters that actually constitute it. That process of deduction from indirect evidence is one of the most powerful tools science has ever developed. It is the same reasoning that allowed Newton to deduce the existence of gravity from the motion of the moon, and the same reasoning that allowed astronomers in the 19th century to predict the location of Neptune before a single telescope had pointed at it, based purely on the way Uranus was wobbling ever so slightly off course. The Great Attractor adds a chapter to that tradition, the tradition of finding hidden things by carefully reading their effects on the visible world. We know its address now, and we know its mass, and we know the direction it is pulling us and the speed at which we are being pulled. We know that the Great Attractor is itself just one node in a web of influence that extends to the edge of what we can measure, a web that you are physically part of, because your atoms are in motion toward the Great Attractor right now. Tonight we learned something about where you are going. Before we can understand the Great Attractor, we need to establish where it sits in the hierarchy of cosmic structure, because the hierarchy itself is worth understanding, and most people have never had reason to think about it carefully. Start with what you know. The Earth orbits the Sun, and the Sun is one of roughly 200 to 400 billion stars in the Milky Way galaxy, a large spiral about 100,000 light-years across. A light-year is the distance light travels in 1 year, about 6 trillion miles, so the Milky Way is 600 quadrillion miles across, a number too large to hold in any intuitive sense. Accept it as very large, and move on. The Milky Way has companion galaxies. The large and small Magellanic Clouds are dwarf galaxies visible from the southern hemisphere, orbiting our own, and the Andromeda Galaxy is a large spiral similar in size to the Milky Way, located about 2.5 million light-years away. The Milky Way, Andromeda, and several dozen smaller galaxies form a structure called the local group, roughly 10 million light-years across. The local group is part of a larger structure still. The Virgo cluster is a dense concentration of roughly 1,300 galaxies centered about 53 million light-years away, and the local group sits near the edge of its gravitational reach. The Virgo cluster and the surrounding region, including our local group, form the Virgo supercluster, also called the local supercluster, about 110 million light-years across, containing roughly 100 galaxy groups and clusters. And the Virgo supercluster is not the end of the hierarchy, not even close. Each time astronomers have looked one level higher, they have found something larger, something more organized, something pulling on everything below it. The Great Attractor is the next level up, and beyond it, as we will see, there is still something larger pulling on it. In 2014, a team led by astronomer Brent Tully used galaxy velocity data to define an even larger structure. They identified the supercluster that contains the Virgo supercluster as a single gravitationally coherent region, and they named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is approximately 500 million light-years across, containing roughly 100,000 galaxies, with a total mass estimated at 10 to the power of 17 solar masses, which is 100 quadrillion times the mass of the Sun. The Great Attractor sits at the heart of Laniakea. It is the gravitational center toward which the entire supercluster flows, and when Tully and his team mapped the velocities of galaxies throughout Laniakea, they found that all the motion converged on a single point. Every galaxy in this enormous structure, including the Milky Way, is moving inward toward that convergence, like water flowing across a vast watershed toward a single drainage basin. The convergence point is located in the direction of the constellation Centaurus, roughly 250 million light-years from Earth. The region is dominated by the Norma cluster, a dense concentration of galaxies also cataloged as a Bell 3627, and behind the Norma cluster, farther still, lies the Shapley supercluster, which we will come to later. It turns out to be even more important than the Great Attractor itself. The scale of the Great Attractor's gravitational influence is what makes it so remarkable. Its gravity is shaping the motion of a volume of space roughly 600 million light-years across, and within that volume, the normal Hubble expansion of the universe, The general outward drift of all galaxies away from each other as space itself expands is being modified. Galaxies that should be moving apart are instead converging on a common center. The Great Attractor is not stopping the expansion of the universe. It is creating a local deviation from it, a flow on top of expansion, pointing inward. Understanding this required a completely new way of thinking about galaxy motion. For most of the 20th century, astronomers assumed that after accounting for Hubble expansion, individual galaxies would have only small random velocities. So the discovery that entire clusters and superclusters were participating in a coherent large-scale flow, all moving together in the same direction at enormous speed. It meant the universe was organized at larger scales than anyone had expected, and it meant there was something out there, massive enough to organize all that motion, waiting to be found. The Laniakea mapping work also changed how scientists define a supercluster. Before 2014, superclusters were defined loosely by galaxy density, and different astronomers drew different boundaries. The new approach defined a supercluster by its velocity field rather than its density, drawing the boundary of Laniakea at the line where inward flow toward the Great Attractor ends and outward flow away from it begins. A physically meaningful boundary that separates matter falling inward from matter drifting away toward other attractors elsewhere in the universe. This redefined the Virgo supercluster entirely. It was no longer independent but rather a smaller structure inside the much larger Laniakea, about 5 times smaller than the new map revealed, and the Virgo cluster, previously considered our dominant local mass concentration, turned out to be a relatively minor feature in the fuller picture. 500 million light-years across, 100,000 galaxies, all moving inward toward a hidden concentration of mass, sitting behind the dust of the Milky Way. Knowing this changes nothing about the night sky as it appears to the naked eye, because the stars look the same and the constellations have not moved. But knowing that the entire sky is being carried together in an enormous coherent flow toward a single hidden destination, that is one of the more vertiginous insights modern cosmology has to offer. The story of how the Great Attractor was discovered is a story about a puzzle that kept getting harder to ignore. It begins in the 1970s with an anomaly in the cosmic microwave background radiation. The cosmic microwave background is the faint afterglow of the early universe, the light left over from about 380,000 years after the Big Bang, filling all of space nearly uniformly at a temperature of about 2.7 Kelvin, just barely above absolute zero. When sensitive detectors began measuring this radiation precisely enough to detect tiny variations, something unexpected turned up. The radiation appeared very slightly warmer in one direction and very slightly cooler in the opposite direction, a dipole pattern whose natural explanation was that the solar system was moving through space in the direction of the warmer side, the motion creating a Doppler shift that compressed the wavelengths ahead of us and stretched them behind. The speed implied by this dipole was roughly 600 kilometers per second. This was unexpected. The universe was supposed to be expanding smoothly and uniformly, so 600 kilometers per second of additional motion in a specific direction was hard to explain. Something was pulling. The question was what? In the early 1980s, astronomers began systematic surveys of galaxy redshifts, trying to map how galaxies were actually moving in the local universe. Redshift is the stretching of light toward longer wavelengths when a source is moving away from you. And by measuring the redshifts of many galaxies, astronomers could determine their recession velocities and compare them to the prediction from Hubble expansion. Any deviation from that prediction revealed the presence of additional gravitational forces at work. What the surveys showed was startling. Hundreds of galaxies across a vast region of space were all drifting in the same direction toward the constellation Centaurus, at speeds that Hubble expansion alone simply could not explain. The flow was not small, and it was not a measurement artifact. It was systematic and large and consistent across multiple independent surveys. In 1986, 7 astronomers published a landmark paper, Alan Dressler, David Burstein, Roger Davies, Sandra Faber, Donald Lyndon Bell, Roberto Terlovich, and Gary Wegner, who became known informally as the Seven Samurai. Their paper presented the most comprehensive evidence yet for a large-scale coherent flow and estimated the mass required to produce it. The mass was extraordinary, requiring a concentration of matter in the direction of Centaurus with a mass tens of thousands of times that of the Milky Way, hidden from direct observation by the zone of avoidance. Alan Dressler gave it its name, the Great Attractor. Not a specific object, not something cataloged and measured, but a region, a gravitational presence, an influence without a face, and it immediately became one of the signature mysteries of modern observational cosmology. The Seven Samurai paper sparked enormous follow-up work. Some groups found smaller or differently directed flows, while others supported the original result, and the debate continued for years, driven by the genuine difficulty of measuring galaxy distances precisely enough to separate true peculiar velocities from measurement error. By the mid-1990s, the consensus had solidified. The flow was real. The Great Attractor was real. And the question shifted from whether it existed to what, exactly, it was. The path to that consensus was not smooth. Even after the Seven Samurai paper, some astronomers remained skeptical, and the disagreements came down to a technical problem at the heart of the measurement. How do you know how far away a galaxy actually is? How do you separate genuine peculiar motion from the noise of imprecise distance estimates? Those questions drove the debate for nearly a decade, and answering them required building better tools, gathering larger samples, and developing more sophisticated statistical methods. The answer eventually came, but it took time. To measure a peculiar velocity, you need to know a galaxy's true distance independently of its redshift, and several methods exist for this. The Tully-Fisher relation links the rotational speed of a spiral galaxy to its intrinsic brightness, while the fundamental plane connects the size, surface brightness, and internal velocity of elliptical galaxies to their true luminosity. Type Ia supernovae, exploding stars that reach a known peak brightness, serve as standard candles across cosmic distances. Each method has its own uncertainties, and different methods applied to the same galaxy can give distances that differ by 10 to 20%. A 10% distance error translates directly into a large peculiar velocity error, so early surveys had enough uncertainty that the existence of a large bulk flow could genuinely be questioned. As methods improved and sample sizes grew through the 1990s and 2000s, the uncertainties shrank, and the bulk flow toward the Great Attractor region became harder and harder to dismiss. By the time the Cosmic Flows Project, led by Brent Tully and colleagues, began producing systematic surveys of galaxy velocities in the 2000s and 2010s, the Great Attractor had been firmly established. Those surveys used multiple distance indicators applied to thousands of galaxies, producing the most precise maps yet of the local velocity field. And they confirmed and refined the picture the Seven Samurai had first sketched 3 decades earlier. The flow is real, the source is real, and the Great Attractor sits exactly where the velocity field says it should. The story of the Great Attractor's acceptance is a useful case study in how science handles controversial findings, not by immediate consensus, but by accumulation, method after method, survey after survey, each with different systematic errors, all converging on the same picture over time. The legacy of the Seven Samurai paper extends well beyond its specific conclusions. It showed that cosmology could make progress on large-scale structure by studying peculiar velocities directly, a method that has since become a major research program. And the Cosmic Flows surveys, the 60F Galaxy Survey Peculiar Velocity Sample, and other modern efforts are all descended from the approach Dressler, Faber, and their colleagues pioneered. The Great Attractor problem opened a field of inquiry that is still producing new results today. To understand why the Great Attractor is remarkable, it helps to understand what galaxies are normally supposed to be doing. The universe is expanding, and this has been known since Edwin Hubble published his observations in 1929. Hubble found that galaxies were receding from us, and that more distant galaxies were receding faster, in a relationship now called Hubble's law. The interpretation is that space itself is expanding, that galaxies are not flying through space away from us, but rather that the space between them is growing, carrying them apart the way dots on a balloon move apart as you inflate it. In this framework, every galaxy should be receding from every other at a rate proportional to the distance between them, which is called the Hubble flow. For any galaxy at a known distance, you can calculate the expected recession velocity, and if the actual velocity differs from that expectation, the difference is called the peculiar velocity, the real motion through space caused by gravitational interactions, over and above the general expansion of space. The motion of the Milky Way toward the Great Attractor is a peculiar velocity, 600 kilometers per second, pointing with remarkable consistency toward a single region of sky, confirmed by multiple independent measurement methods. To produce that peculiar velocity from that distance, the mass concentrated in the Great Attractor region must be truly enormous, and early estimates placed it around 10 million billion times the mass of the Sun, while later analyses revised those estimates upwards still further. The basic conclusion remains: the Great Attractor is one of the largest concentrations of mass in the observable universe. The peculiar velocity is not unique to the Milky Way, because every galaxy in a vast surrounding volume shares this motion. The Andromeda Galaxy is moving with us, and the entire local group is moving with us, and the Virgo cluster is moving with us, and the Virgo supercluster is moving with us. All of these structures containing hundreds of thousands of galaxies, all participating in the same coherent flow toward the same destination. When you map the velocity vectors of galaxies across a region several hundred million light-years in extent, they all point inward toward the convergence zone near the Norma cluster. This kind of large-scale coordinated motion is called a bulk flow. Cosmological theory predicted that bulk flows would exist because the uneven distribution of matter across the universe creates gravitational gradients, hills and valleys in the fabric of space, that push and pull galaxies into correlated motion. But the scale of the flow associated with the Great Attractor was larger than early theories anticipated, implying more mass, at greater distances, more concentrated, than the standard models of the day had predicted. In this sense, the Great Attractor was not just a discovery about one object. It was evidence that the universe is organized at scales we had not yet mapped. The pull of the Great Attractor raises an obvious question. If we are being pulled toward it at 600 kilometers per second, will we eventually arrive? Will the Milky Way someday fall into this enormous concentration of mass? The answer, as we will explore later, is complicated by the expansion of the universe. The short version is that we are being pulled toward the Great Attractor, but the universe is also expanding away from it, and whether gravity wins or expansion wins depends on the relative magnitudes of those two effects. The current answer is that we will very likely never arrive, but the reasons for that are themselves worth understanding. The concept of peculiar velocity deserves a moment more attention, because it sits at the center of everything in this story. In a universe governed purely by Hubble expansion, measuring the velocity of a galaxy would immediately tell you its distance. More distant galaxies recede faster. The relationship is linear, and you would just measure the recession velocity, divide by the Hubble constant, and have the distance. Peculiar velocities break this relationship entirely, because a galaxy moving toward us at several hundred kilometers per second will appear to recede more slowly than its true distance would predict, making it look closer than it actually is, while a galaxy moving away from us faster than average will look farther away than it really is. This contamination of the redshift-distance relationship by real motion through space is called redshift space distortion, and it is one of the main complications in mapping the three-dimensional universe. For the Great Attractor problem, the relevant peculiar velocities are large. 600 kilometers per second is about 6% of the total recession velocity at the distances involved, which is not negligible, and it is large enough to produce clearly anomalous patterns in the data. Patterns that the Seven Samurai and others saw plainly in their surveys and spent years trying to explain. The anomalous pattern was the clue. Galaxies moving faster or slower than Hubble law predicted in a coherent systematic pattern pointing toward a single hidden source, and translating that pattern into a mass estimate and a location required careful modeling and years of work. The result was the Great Attractor. One of the most frustrating aspects of the Great Attractor, for the astronomers who study it, is that it sits in one of the most difficult regions of sky to observe. The Great Attractor lies behind the zone of avoidance, which is the evocative name for the band of sky that corresponds to the plane of the Milky Way. When you look in the direction of the galactic plane, your line of sight passes through the full thickness of our galaxy, through enormous quantities of gas and dust, and that dust absorbs and scatters light, blocking the view of anything behind it. In the optical wavelengths where most astronomical observation was done historically, roughly 20% of the sky is obscured by the zone of avoidance to varying degrees, and near the galactic center, the most heavily obscured regions are effectively opaque. The Great Attractor happens to lie almost exactly in the direction of the galactic plane, an accident of geometry rather than any physical relationship. The Great Attractor is hundreds of millions of light years away, while the dust blocking our view of it is within a few thousand light years, right here inside our own galaxy. But the effect is the same as if someone had placed an enormous frosted glass screen between us and the most important gravitational structure in our local universe. The Norma cluster, at the core of the Great Attractor region, sits at a galactic latitude of about -7 degrees, meaning it is extremely close to the plane of the Milky Way and well within the zone of avoidance from most optical wavelengths. Studying it in visible light from Earth is nearly impossible. This is why the Great Attractor went undiscovered for so long, despite being the dominant gravitational influence on everything around us. You cannot see it. You can only infer it from its effects on things you can see, and the Seven Samurai did not observe the Great Attractor directly. They measured the velocities of galaxies they could observe and deduced from the pattern that something massive was sitting in the hidden zone, pulling everything toward it. The solution came from moving beyond optical astronomy, because radio waves and X-rays pass through galactic dust far more easily than visible light, and infrared wavelengths are also less affected by dust absorption. Beginning in the 1990s, astronomers used these wavelengths to peer into the zone of avoidance and map what was hidden there. What they found confirmed the predictions. The Norma cluster is a rich, dense cluster full of elliptical galaxies and hot X-ray emitting gas, and beyond it, surveys revealed additional galaxy concentrations that had been completely unknown, invisible behind the dust curtain. The most dramatic finding was the discovery of what is now called the Norma Wall, or sometimes the Great Attractor Wall, a vast sheet of galaxies running through the zone of avoidance, connecting multiple clusters, extending over an enormous volume. It was one of the larger structures in the local universe, completely unknown until the right instruments were pointed in the right direction. The zone of avoidance is no longer the complete barrier it once was. Modern near-infrared surveys can penetrate much of the dust, and the Great Attractor region has been mapped in considerable detail. What was once purely inferred has now been directly observed, and the Norma cluster is a real object with measured properties. The mystery has not been fully solved, but it has been substantially demystified, and what was once a blank space on every map of the local universe has become one of the better studied regions of the large-scale structure, precisely because so many astronomers were motivated to look more carefully at the place they could not easily see. The Great Attractor hid itself well. but it could not hide forever. The practical implications of the zone of avoidance extend beyond the Great Attractor problem, because any survey of the large-scale structure of the universe has a gap where the galactic plane blocks the view. And that gap affects our understanding of the total matter distribution around us and introduces systematic uncertainties into cosmological measurements. Our estimates of how much matter is in the local universe and how it is distributed are based on an incomplete picture. The missing region is not random but a coherent band aligned with the galactic plane. And if large structures are hidden there, they introduce biases into analyses that assume the visible sky is representative of the whole sky. The Great Attractor region was itself a victim of this bias for decades. The enormous mass concentration in the Norma cluster and surrounding structures was simply absent from sky surveys because the dust hid it, so estimates of the local mass distribution were systematically too low in that direction. The full sky surveys in infrared and radio wavelengths corrected this, but the history is a clear illustration of the problem. Modern surveys have reduced the extent of the truly unknown zone of avoidance considerably. The WISE satellite survey, the 2-mass extended source catalog, and various radio surveys have now covered most of the galactic plane at wavelengths where extinction is manageable. And the remaining blind spots are mostly within a few degrees of the galactic center in the densest dust. For the Great Attractor region, about 7 degrees from the plane, the coverage is now substantial, and the residual uncertainties are now about completeness rather than total obscuration. Every map of the universe that astronomers have ever made has this gap running through it, like a scar, a band across the sky where the data becomes unreliable or absent. For most of the history of observational astronomy, this gap was simply accepted because you could not see through your own galaxy, so you worked with what you could see and noted the limitation. The other side of the dust was unknown territory. The zone of avoidance is not uniformly opaque. Near the galactic poles, the line of sight passes through relatively little dust and transparency is good, while near the galactic center even powerful instruments struggle to see through. At intermediate latitudes the obscuration varies, and in some directions windows of lower extinction allow partial views of the background universe beyond. This matters for the Great Attractor because it sits in the most obscured part of the sky, so estimates of its mass and location depend on indirect evidence, on the measured velocities of galaxies that can be observed and on models of how those velocities relate to the underlying mass distribution. Those estimates have improved enormously as data has accumulated, but they still carry uncertainties that would be smaller if the Great Attractor lay at high galactic latitude, where we could study it directly. The progress made in penetrating the zone of avoidance is one of the genuine successes of modern observational astronomy. The Glimpsey survey used the Spitzer Space Telescope to map the galactic plane in infrared light, revealing thousands of previously unknown star clusters and star-forming regions. The 2-micron all-sky survey produced the first near-infrared map of the entire sky, detecting galaxies through the zone of avoidance that are completely invisible in optical light. The H.I. Parkes all-sky survey used radio emission from neutral hydrogen to map galaxy positions behind dust that blocks all optical and near-infrared light entirely. These surveys transformed what we know about the galaxy distribution near the galactic plane, revealing that the zone of avoidance contains a substantial fraction of the mass in our cosmological neighborhood. The story of the zone of avoidance is also a reminder about the contingent nature of scientific knowledge, because what we know about the universe is shaped partly by where we happen to be sitting inside it. An observer in a different galaxy, with a different orientation of their galactic plane, would have a different zone of avoidance, and they might have a clean line of sight to exactly what we cannot see. They might have discovered the Great Attractor centuries before we did, simply because the geometry of their location gave them a clearer view. We are not uniquely disadvantaged. Every observer in every galaxy has their own zone of avoidance, their own blind spot created by the plane of their own galaxy. But the particular accident of our galactic orientation has placed our largest local gravitational structure squarely behind our most opaque visual barrier. That is the kind of detail that makes the history of science feel less like a march of inevitable progress and more like a negotiation with contingency. The zone of avoidance has also been the site of surprising discoveries that had nothing to do with the Great Attractor, because some of the most interesting objects in the local universe were found only when astronomers developed tools to see through the galactic plane. The Ophiuchus supercluster is one example, a massive galaxy cluster located at moderate distance behind the galactic plane, known as a diffuse X-ray source for years before its true nature as a galaxy cluster was confirmed by infrared observations. It turns out to be one of the more massive clusters in the local universe, with properties that make it a significant object in its own right. The Vela supercluster is another. Discovered in 2017 by a team using the Anglo-Australian telescope, located about 800 million light-years away and sitting partly behind the zone of avoidance, it had gone completely unnoticed by previous surveys despite its large mass and relative proximity, because obscuration hid most of its galaxy content. When it was found, it immediately became one of the largest known structures in the local universe. These discoveries illustrate how much of our cosmological neighborhood remains to be characterized, and the tools we have now are far better than those available in 1986, when the Great Attractor was named. But they are not perfect. The universe still has structures waiting to be found, hiding behind our own galaxy, or at distances where current surveys are simply incomplete. And each new generation of instruments reveals something the previous generation missed. The zone of avoidance is therefore not merely a historical obstacle to studying the Great Attractor, but an ongoing frontier, because the next generation of radio surveys, infrared missions, and gravitational wave observatories will peer deeper into the obscured sky and reveal structures that are currently unknown. Some of those structures may be contributing to the velocity field of the Milky Way in ways we have not yet accounted for, which means that our picture of what is pulling us, and from where, is almost certainly not yet complete. As astronomers mapped the Great Attractor region more carefully, they made a discovery that complicated the picture considerably. The Great Attractor was not the only thing pulling on the Milky Way, because something even larger was pulling on the Great Attractor. The Shapley supercluster is the most massive structure in the local universe, located approximately 650 million light-years away in the direction of Centaurus, roughly in line with the Great Attractor, but 2.5 times farther. It was first catalogued by the astronomer Harlow Shapley in 1930, when he noticed an unusual concentration of galaxies in that region, though at the time the significance of the concentration was not appreciated. By the 1990s, as large-scale structure surveys accumulated more data, the Shapley supercluster began to look more important than anyone had realized. It is a massive concentration of galaxy clusters, containing roughly 30 rich clusters and dozens of smaller groups, with a total mass estimated at around 10 to the power of 17 solar masses, comparable to or exceeding the mass of the Great Attractor region. It is visible in the galaxy distribution data as a pronounced overdensity, a region where galaxies are far more tightly packed than average. The question that arose was whether the Shapley supercluster was contributing significantly to the bulk flow observed in our neighborhood. The Great Attractor had been assumed to explain all of the Milky Way's peculiar velocity, but some analyses suggested it was not sufficient. The residual velocities, after removing the Great Attractor contribution, still showed a component pointing roughly in the same direction, toward Centaurus and beyond. Research from the 2000s onward has increasingly supported the view that both the Great Attractor and the Shapley supercluster are contributing to our motion, and roughly half of our 600 km/s peculiar velocity may be attributable to the pull of the Shapley supercluster, acting from twice the distance of the Great Attractor, while the other half comes from the Great Attractor and the surrounding structures. This means the story of what is pulling us is more layered than the original picture suggested. We are not simply falling toward one massive object, but rather being pulled by a hierarchy of structures at different distances and different scales, all roughly aligned in the same direction because they are part of the same large-scale filament structure of the cosmic web. The Shapley supercluster itself sits at the convergence of several enormous filaments, a node where multiple large-scale structures intersect, and its extraordinary mass is the result of matter accumulating at that intersection over billions of years. Understanding the Shapley supercluster required the same kinds of redshift surveys and velocity analyses that revealed the Great Attractor, but extended to greater distances and requiring more precise measurements. The picture that has emerged is one of nested influence. The Great Attractor pulls us, and the Shapley supercluster pulls the Great Attractor and us simultaneously. And beyond the Shapley supercluster, at even greater distances, there may be additional structures contributing smaller components to our net motion. Cosmologists call this the velocity field, and mapping it accurately requires precise distance measurements for galaxies across enormous volumes of space. For the Milky Way, the two dominant external gravitational influences are the Great Attractor, roughly 250 million light-years away, and the Shapley supercluster at roughly 650 million light-years. Gravitational acceleration decreases with the square of distance, so a more distant object needs to be much more massive to produce the same effect as a closer one, and the Shapley supercluster is about 2.5 times farther than the Great Attractor, meaning it needs to be roughly 6 times more massive to produce the same gravitational contribution. The estimates suggest it is comparably massive, which is why both sources matter. Beyond both of them, additional structures at even greater distances contribute smaller pieces to the overall flow. And the full picture is that the Milky Way is embedded in a complex gravitational landscape, being pulled by many things simultaneously. The 600 kilometers per second we measure is the vector sum of all those influences, the accumulated fingerprint of the large-scale structure of the universe written in our motion through space. No discussion of the Great Attractor is complete without confronting dark matter, because the mass required to produce the observed gravitational effects cannot be accounted for by the visible matter alone. Dark matter is one of the central puzzles of modern physics. Multiple independent lines of evidence indicate that the universe contains roughly 5 times as much matter that does not interact with light as matter that does, and we cannot see dark matter directly. It emits no light, reflects no light, absorbs no light. It is dark in the most literal sense, but it has mass, and mass creates gravity, and gravity affects the motion of everything around it. We infer it the same way we infer a strong wind by watching leaves move rather than by seeing the wind itself. The evidence for dark matter comes from many directions at once. The rotation curves of spiral galaxies stay flat at large radii when they should decline, indicating extra unseen mass in galactic halos. Galaxy clusters contain far more mass than their visible content suggests, as measured by gravitational lensing, and by the temperature of the hot gas they contain. The cosmic microwave background power spectrum is consistent with a universe containing about 27% dark matter by mass energy content, and structure formation models require dark matter to produce the galaxies and clusters we observe. The Great Attractor is a dark matter structure as much as it is a visible galaxy concentration. The enormous mass that creates the gravitational pull we are moving toward is dominated by dark matter, and the visible galaxies, stars, gas, and dust in that region are the luminous fraction, roughly 20% of the matter present, floating in a much larger invisible halo that extends far beyond anything we can directly observe. This means that maps of the galaxy distribution in the Great Attractor region, even the best available from modern surveys, are showing us only a biased tracer of the underlying mass. The galaxies tell us where the dark matter probably is, because galaxies form preferentially in regions of high dark matter density, but the dark matter halos are larger than the visible galaxy distributions suggest, and the total mass is substantially higher than you would estimate from counting galaxies alone. The composition of dark matter remains unknown. Candidates include weakly interacting massive particles, actions, and primordial black holes, and none has been directly detected despite extensive experimental searches. The dark matter remains dark, in both the literal and the metaphorical senses. What we can say is that whatever dark matter is, it was present from very early in cosmic history, and has been the dominant driver of structure formation ever since. The Great Attractor exists because dark matter began clumping gravitationally in the early universe, and ordinary matter followed, forming galaxies inside the dark matter potential wells. The same physics that produced the first galaxies, acting over billions of years, produced the enormous structures we see today. The standard cosmological model holds that the universe began in an almost perfectly smooth state, with the tiny density fluctuations present at very early times being quantum fluctuations, frozen into the fabric of space-time during a period of rapid early expansion called inflation. After inflation, those small fluctuations began growing under gravity. Regions slightly denser than average attracted more matter from their surroundings, and the matter that fell in made them denser still, which attracted more matter, a runaway process of gravitational collapse that acted over billions of years to produce the structures we see today. The Great Attractor is one of the more massive nodes in the local cosmic web, and the seed that became it was a small density fluctuation in the early universe, perhaps just a fraction of a percent denser than average, growing over billions of years into one of the dominant mass concentrations in our cosmological neighborhood. Dark matter was essential to that growth, because without it, ordinary matter would not have had sufficient time to form the structures we observe. The gravitational amplification process is much slower for ordinary matter alone, since ordinary matter interacts with radiation and was prevented from clumping freely in the very early universe. Dark matter, which does not interact with radiation, began clumping earlier and more freely, building the halos that ordinary matter subsequently fell into, and so the Great Attractor, like every large structure in the universe, is fundamentally a dark matter structure with visible galaxies as its luminous decoration. The search for dark matter particles continues across multiple experimental fronts. Underground detectors in deep mines attempt to catch the rare collision of a dark matter particle with an atomic nucleus. Particle accelerators attempt to produce dark matter in high-energy collisions. Space telescopes search for gamma-ray signatures that might indicate dark matter annihilation in dense halos. None of these searches has yet produced a confirmed detection, and the dark matter remains elusive at the particle level while being unmistakably present at the cosmological level. The Great Attractor is one of the most massive dark matter structures within our cosmological reach, and understanding it better may eventually help constrain what dark matter actually is. To place the Great Attractor in its full context, we need to step back further still and look at the largest structures in the observable universe. The universe is not a uniform fog of galaxies, but is organized into an intricate pattern called the cosmic web. On scales of hundreds of millions of light years, galaxies are arranged in a network of filaments and sheets, separated by enormous empty regions called voids, and the filaments intersect at nodes where galaxy clusters and superclusters concentrate. The voids between the filaments contain very few galaxies and very little matter of any kind. This pattern was first glimpsed in the 1980s, when early redshift surveys began mapping galaxy positions in 3 dimensions. The Center for Astrophysics Survey, conducted by Margaret Geller, John Huckra, and colleagues in the late 1980s, revealed the first clear images of the large-scale structure, showing a striking pattern of walls and voids that looked, to many observers, like the surface of soap bubbles, or the interior of a sponge, a 3-dimensional network of filaments enclosing nearly empty cells. Later surveys with better instruments and larger samples confirmed and refined this picture. The Sloan Digital Sky Survey mapped over 1 million galaxies across a significant fraction of the sky, producing three-dimensional maps of the large-scale structure in extraordinary detail, and the patterns are consistent with the standard cosmological model, which explains the cosmic web as the product of gravitational amplification of tiny quantum fluctuations from the very beginning of cosmic time. The Great Attractor sits at the intersection of several large filaments in the cosmic web. The Norma cluster, the Centaurus cluster, and the surrounding structures are nodes on this web, points where multiple filaments meet and matter has accumulated over billions of years. And the motion of the Milky Way toward the Great Attractor is the motion of a small group flowing along a filament toward the node at its terminus. Matter in the cosmic web moves along the filaments toward the nodes. And this is how structures grow. The Great Attractor has been accumulating matter by drawing galaxies along the filaments that connect to it for billions of years, and it will continue doing so as long as gravity operates and matter remains available to flow. The voids are the complement of the filaments, regions emptied of matter by gravity, their content having flowed outward along the filaments into the dense structures. They are not truly empty, containing a small residual density of dark matter and a sparse population of dwarf galaxies, but compared to the filaments in clusters they are nearly vacant, and they are enormous. Typical voids in the local universe have diameters of 100 to 300 million light-years. The Milky Way is not located in a void. It sits in a relatively ordinary part of the cosmic web, the local group nestled in a filament that connects to the Virgo cluster and ultimately to the Great Attractor, and our position is neither privileged nor unusual. We are one small group among many, flowing along the structure of the web toward the massive nodes that gravity has assembled at the intersections. Understanding the cosmic web requires accepting that the universe, despite being governed by simple physical laws, has organized itself into structures of extraordinary complexity and beauty. The same gravitational physics that holds you to the Earth and keeps the Moon in orbit has, acting over billions of years and across the full scale of the observable universe, assembled this vast intricate web. The Great Attractor is not an anomaly. It is the web doing what the web does, organizing matter, pulling things inward, building structure from the bottom up. The cosmic web is not static, but is evolving, and the direction of that evolution is toward greater concentration and greater emptiness simultaneously. In the dense nodes and filaments, matter continues to accrete. Galaxy clusters grow as galaxies fall into them along the filaments, and superclusters accumulate mass at their centers, with the most massive nodes, like the Great Attractor and the Shapley supercluster, becoming progressively more dominant over time. In the voids, the opposite is happening. They grow emptier as matter that was once there flows outward along the filaments into the dense structures, and the voids expand as the filaments that border them grow thinner and more concentrated. In the very long-term future, if the universe continues to expand with accelerating dark energy, the voids will dominate, and expansion will carry the distant filaments and clusters beyond the reach of local gravity, leaving each bound structure increasingly isolated in an emptying cosmos. The Great Attractor is a feature of the present phase of cosmic evolution. In the very distant future, billions of years from now, the structures we call superclusters will be partially or fully disrupted by the accelerating expansion. The local group will remain bound to itself and possibly to the Virgo cluster. But Laniakea as a whole will cease to be coherent as expansion carries its outer members beyond the gravitational boundary, and the flow toward the Great Attractor that defines it will gradually break down. This is not a catastrophe. It is simply the evolution of structure under the competing influences of gravity and dark energy, and every cosmological structure has a lifespan. Galaxies formed, groups formed, clusters formed, superclusters formed, all over billions of years of gravitational amplification, and in the far future dark energy will reverse the process at the largest scales. leaving bound structures as isolated islands in an increasingly dark and empty expanding universe. For now, we are in the epoch when these grand structures exist and flow and organize. The Great Attractor is real and active and pulling everything around it, and we are living in the moment of the cosmic web's maturity, from which we can see both what the universe has built and the forces that will eventually dismantle its largest features. The Milky Way is being pulled toward the Great Attractor at 600 kilometers per second, and the obvious question this raises is, given enough time, will we get there? Before we can answer that, it helps to understand one more piece of the picture, which is the role of dark energy in shaping the long-term fate of large-scale structure. Dark energy is the name astronomers give to the mysterious force that is causing the expansion of the universe to accelerate. And its existence means that the competition between gravity and expansion is not a static one. Gravity pulls things together. Dark energy pushes them apart. And on different scales and at different distances, these two forces produce very different outcomes. Within a galaxy, gravity wins easily. Within a supercluster, the outcome depends on exactly how much mass is concentrated and how far apart the pieces are. And the answer turns out to matter enormously for whether structures like Laniakea will survive or dissolve. The answer requires understanding the competition between gravity and the expansion of the universe. The expansion operates on all scales, but its effects are only noticeable on scales larger than the gravitational binding scale of the structure in question. Within a galaxy, gravity easily overcomes expansion, and the galaxy holds together. Within a galaxy cluster, gravity overcomes expansion, and the cluster holds together. Within a supercluster, the situation is more complicated because superclusters are not gravitationally bound in the way that clusters are, and the gravity of a supercluster is not strong enough to overcome the expansion of the universe across its full extent. This distinction is crucial for understanding the fate of the Milky Way relative to the Great Attractor. Laniakea as a whole is not a gravitationally bound structure, but rather a transient configuration, a region currently flowing inward that will not ultimately collapse into a single bound object. The expansion of the universe is accelerating, driven by dark energy, and this acceleration is gradually pulling apart structures that are not tightly bound. The Milky Way and surrounding structures are falling toward the Great Attractor at 600 kilometers per second, but the Great Attractor itself, and the Shapley supercluster, and everything else in our cosmological neighborhood are simultaneously being carried away by the expansion of space. The recession velocity due to expansion increases with distance, and at the distance of the Great Attractor, the expansion velocity is already substantial. In practice, we are approaching the Great Attractor in terms of peculiar velocity, our actual motion through space, but we may or may not be closing the gap in physical distance because the expansion of space is adding distance at the same time. Current calculations suggest expansion will win for most of Laniakea, with the outer regions eventually being carried away and disconnected from the center. The inner regions, close enough to the Great Attractor, may ultimately fall together, but the Milky Way at its current distance is likely in a borderline region where the outcome is uncertain on timescales of tens of billions of years. Even if the Milky Way is gravitationally bound to the Great Attractor region, the timescale for any meaningful approach is immense. At 600 kilometers per second, covering 250 million light-years would take about 1.25 billion years, and that assumes the distance is not also growing due to expansion. Accounting for the full dynamics of the system, any meaningful merging with the Great Attractor region would take tens of billions of years, if it happens at all. Before that, other events will intervene. The Milky Way and Andromeda are gravitationally bound to each other and will merge in roughly 4.5 billion years, and the Sun will exhaust its hydrogen fuel and swell into a red giant in about 5 billion years. The timescales of stellar evolution and galactic mergers are much shorter than any encounter with the Great Attractor. So the answer is, probably not, in any meaningful sense. The Great Attractor is pulling us, and we are moving toward it. But the universe is also expanding. The timescales are enormous, and the events of our own galactic history will unfold long before any approach to the Great Attractor becomes relevant. The expansion of the universe introduces one more layer worth examining. The universe is not just expanding but accelerating in its expansion, a fact established in the late 1990s and attributed to dark energy, a form of energy inherent to space itself that pushes outward against gravity. The nature of dark energy is one of the deepest unsolved problems in all of physics. We know it exists because of its measured effects on cosmic expansion, but we do not know what it is at a fundamental level. The acceleration changes the long-term fate of the universe dramatically. In our actual accelerating universe, the expansion continues indefinitely. Distant galaxies are being carried away faster and faster, and galaxies beyond a certain distance, called the cosmic event horizon, are moving away faster than the speed of light and can never be observed or reached. For the Great Attractor, this means its gravitational influence is racing against cosmic expansion. And while the Great Attractor's gravity is currently winning at the scales relevant to Laniakea, this will not always be the case. The outcome will play out over timescales that dwarf the entire history of life on Earth. There is a version of the Great Attractor story that is purely technical, about anomalous galaxy velocities and peculiar motion fields and mass concentrations and gravitational potential wells, a story about measurements and models, and the slow accumulation of evidence for a large-scale structure hidden behind the dust of our own galaxy. But there is another version of the story, and that is the one worth sitting with tonight. You live on a planet. The planet orbits a star. The star is one of several 100 billion stars in a galaxy. The galaxy is one of roughly 100,000 galaxies in a supercluster, and the supercluster is flowing, along with everything in it, toward a gravitational center 250 million light-years away. That center is itself being pulled by something even larger, a mass 650 million light-years distant, called the Shapley supercluster. This is your cosmic address. Not just the planet and the star and the galaxy, which are the parts most people know, but the full address including the supercluster and its motion, and the direction it is flowing, and the thing it is flowing toward. You are not simply located somewhere. You are located somewhere that is going somewhere, because the universe is not a static arrangement of objects sitting in fixed positions. It is a dynamic system of flows and structures, all in motion, all influenced by everything else. Knowing the Great Attractor exists changes how the night sky looks, if you let it. When you look toward Centaurus on a clear night, you are looking toward the gravitational center of your supercluster, looking in the direction you are moving, not the direction you feel yourself moving, lying still in the dark, but the direction your galaxy is moving, pulled by 250 million light-years of accumulated mass, toward a destination that expansion may ultimately prevent you from reaching. The Great Attractor is a reminder that scale matters. The objects visible to the naked eye, the moon, the planets, the stars of the Milky Way, are the small-scale features of a universe organized at scales 1,000,000 times larger, and the large-scale features, the cosmic web, the superclusters, the Great Attractor, are invisible without instruments. But they are real, and their reality shapes everything about the context in which we exist. The discovery of the Great Attractor required a new kind of humility. Not just the Copernican humility of knowing we are not at the center of the solar system, and not just the galactic humility of knowing our solar system is not at the center of the Milky Way, but a deeper humility, the recognition that even our galaxy is a small piece of a much deeper velocity field, that the universe has structure at scales we are only beginning to map. The 7 samurai who identified the Great Attractor in 1986 were trying to solve a specific technical problem about anomalous galaxy velocities, and they were not, in the moment of doing the analysis, contemplating the philosophical implications of what they were finding. But the implications were there. The discovery that we are all moving together toward an invisible hidden mass concentration is one of the most profound additions to our understanding of the cosmos in the last 50 years. And it did not make the news the way a comet or a black hole image might, but it changed our address in the universe, gave us a destination, and told us that the stillness of the night sky is a beautiful and complete illusion. As you lie in the dark tonight, you are moving through space at over 1,000,000 miles per hour, the combined motions of Earth's orbit, the solar system's galactic orbit, and the Milky Way's peculiar velocity all adding together. You feel none of it. The stillness of the room is real at the scale of your body, but it is an illusion at the scale of the galaxy. In the direction of Centaurus, hidden behind the dust of the Milky Way, something enormous is waiting. It has been pulling at everything around it for billions of years, and it will keep pulling long after every star now visible in the night sky has ended. And you, and the planet you are on, and the sun above you, and every other star in this galaxy, are all, quietly and continuously, moving toward it. Sleep well. You are going somewhere remarkable, and you have a very long ride ahead of you. The Great Attractor also carries a lesson about the relationship between what we can see and what is real. For most of human history, the sky was the universe, and what you could see with your eyes was the extent of what you could know. Then the telescope extended the horizon, and then spectroscopy revealed the chemical composition of distant objects, and then redshift measurement revealed recession velocities and cosmic distances. Each step extended the boundary of the knowable universe farther than it had been before. The Great Attractor extended that boundary not by seeing farther, but by reasoning more carefully from what was already visible. Nobody saw it. Astronomers measured the velocities of galaxies they could see, found a pattern in those velocities, and deduced the existence of something hidden that was causing the pattern. The discovery was, at its core, an exercise in inference. The evidence was indirect, the reasoning was careful, and the conclusion was correct. This mode of discovery is becoming increasingly important as science pushes into regimes where direct observation is impossible. Dark matter is known only through inference, the interior of black holes is known only through theory, and the state of the universe before inflation is known only through the traces it left in the structure we observe today. The Great Attractor fits this tradition perfectly. You cannot see it. You can know it. The knowledge that we live inside an enormous flowing structure, pulled toward a gravitational center we cannot directly observe, is one of the more quietly extraordinary facts about our situation. It does not change anything about daily life, because the pull of the Great Attractor is imperceptible at human scales. But it changes the answer to the question of where we are. We are not just on a planet in a solar system in a galaxy, but part of a supercluster, in motion toward a hidden mass concentration 250 million light-years away, in a universe that has been pulling itself together and pushing itself apart simultaneously for nearly 14 billion years. That is an extraordinary place to be, and the ordinary miracle of being here to know it, to lie in the dark and hold that picture, even imperfectly, even incompletely, is worth something. The Great Attractor has been pulling at everything in our neighborhood for billions of years, indifferent to whether anything knew about it. We know about it now. We are the part of it that is aware of the pull. That awareness changes nothing about the physics. The Great Attractor will keep pulling whether or not any consciousness in any galaxy ever notices, but it changes something about what it means to be here, at this particular moment in cosmic time, awake enough to ask the question, and patient enough to listen to the answer. Sleep well. The universe is moving around you, and it is magnificent.